Good afternoon, everyone. Welcome back. My name is Manesh Patel, and we'll get started with the third module in our series in just a minute. We do have a tight schedule today, so due to those constraints, to better get to your questions, please do type them into the chat, and the staff will get to them as soon as they can. Do not forget, you can also email questions as well. And if we do run out of time to answer questions verbally after each presentation, we will try and get to them at the end of the module. Here's part one of the agenda for module 3. Today we'll be tying into what was presented in the two prior modules and apply that information to reviewing projects. We have how to review a project 1, which will be presented by Anthony Roblick along with myself. And we have how to review a project 2, which will be presented by Changyi Wu. After the how to review a project presentations, Peter Plianthos will continue on with groundwater mounding, along with examples of performing the analysis that is required. Then we will have quiz number 3, and if time permits, we will briefly cover some of the common issues we have seen in designs. And if not, we will provide those slides for reference. So let's get started. I, along with Anthony, who will take over in the second half of this presentation, are going to be going through part 1 of how to review a project. This presentation came about because our review of approved projects during compliance audits showed that projects were being approved even though the calculations and stormwater management reports submitted for local approvals did not comply with the stormwater management rules and the local stormwater control ordinances. Therefore, should these projects fail, the municipalities involved would be in violation of their respective permits. So here are the goals of this presentation, which are, by no coincidence, the goals of a successful project review. We want reviewers to be able to identify the design and performance standards that must be met on site, review applications for compliance with green infrastructure, stormwater quantity, stormwater quality, groundwater recharge standards, and review BMPs for compliance with the design criteria found in the BMP manual. The information required in the stormwater report is specified in the stormwater control ordinance, and checklists are available to help with this review. The reviewer must make sure that any information found missing from the report must be added before approval of the project. The checklist found at this link in the Tier A guidance document can help with your review of the report and help to just organize your observations and comments. Now we're going to look at what the reviewer needs to be looking for in the stormwater management report. The first step in the project review is to check if the application package is complete. All the items listed here must be part of the application. So you have pre and post site and grading plans, they're essential, as are the associated calculations and any drainage area maps. The details in the report section should match up with the information on all the plan pages. Too often we find that some parts or even all of the stormwater report does not match the site and grading plans because the report was copied from another project. So the reviewer must also be aware of whether or not the permittee has a more stringent standard of what must be in an application for approval. If so, the reviewer should be looking at all of that information. The township's adopted ordinance, which should be posted online, is also a great starting place to find what information is required to be submitted. Another issue that we see that should be checked right away is that the plans and reports should also be reflected in the maintenance plan so that the BMPs will continue to function as they're designed to be. Too often, we see the maintenance plans submitted that were copied from other projects and do not match at all the project that was submitted. So like I just said, it is important that the reviewer checks that the site description matches up with the plans. The drainage and discharge points all need to be checked along with any change in pervious or impervious coverage. That includes regulated impervious surface and regulated motor vehicle surface for each sub-drainage area. And then also soil information for the site should be included and be accurate. Lisa did cover this, the use of the web soil survey as a means for getting your soil information, and more guidance will be provided later on today. As a side note, print versions of county soil surveys are not always up to date, and they should not be used as your sole resource. The report must include the following information regarding design and performance standards when it comes to what's required, along with any applicable variances, waivers, or exemptions, and how the standards will be met. Again, we find that this is often missing or it does not match up to what is on the plan. So this is very important that this information is provided. The reviewer must be sure that the following calculations are included in the report. Time of concentration, as was discussed in Module 2 last Thursday by Anthony, is essential to characterizing a site. A time of concentration must be calculated and included in the report. Some permittees may require this information be submitted on a CD so that it can be checked and verified. No matter the format, though, it's important to include all of this information, including storm routings, hydrographs, the groundwater recharge spreadsheet, a mounding analysis if it's applicable, and water quality calculations, and make sure it matches what's on the plans. So you saw this slide earlier in Module 1 in the overview presentation. Always check whether the project meets the definition of major development, because there could be the chance that it might not. Also be sure to also check the permittee's definition of major development, as it may be stricter than the department standard. To find that, the reviewer should check the permittee's ordinances. One note here, you need to distinguish the different types of surfaces, whether it be regulated motor vehicle surface, regulated impervious surface, other types of pervious surfaces, and etc. in the report. There are one or more major development thresholds that may apply to the project that the reviewer should be aware of, including the residential site improvement standards, the permittee stormwater control ordinance, and NJDEP land use regulations. As you see here, each has a definition that you need to pay attention to when you're doing a review. Once the reviewer has verified that the required information has been submitted and is accurate, they can begin to actually review the design and performance standards. The plans and report must address the information that's listed here. This information is crucial to determining whether the project was designed properly. Information such as whether the project is discharging to a flood hazard area or a Category 1 waterway are often not included, and therefore they're overlooked during the review. This information may also determine whether or not the project requires input from other agencies, such as NJDEP Land Use or even the Pinelands Commission. Under the current rules, a reviewer must ensure the proposed design complies with the design criteria established in the BMP manual, which in turn ensures the design meets the design and performance standards of the rules. If something is an alternative design or method of calculation, the department must be notified of the approval. Along with the other standards, reviewers must ensure the BMPs follow the green infrastructure standards. And for this, the BMP manual provides the design criteria and considerations for the individual types of green infrastructure BMPs. If the reviewer did allow for waivers or variances, they must be sure that they were applicable. Can waivers or variances even be granted? It's really not a straightforward answer, and to resolve this somewhat gray area, it's better defined in the new rules. The amendments to 7:8-4.6 were made to clarify the conditions that would warrant the granting of a variance by a municipality for a major development project. The amendments are intended to ensure that municipalities are not granting variances under inappropriate circumstances. Municipalities do not have to grant variances, and they do not have to create a mitigation plan if they do not plan to grant variances. But if they do, they can create a mitigation plan that allows the evaluation of mitigation projects suggested by applicants, allowing for the consideration of projects that are submitted by applicants, as is permitted at NJAC 7:8-4.6A3I. With the amended version of the rules, the ability to grant variances requires a little more effort by the applicant. Now, there must be a demonstration that it is technically impracticable to meet one or more of the design standards. And the only allowable variances are for engineering, environmental, or safety reasons, and they have to be spelled out very, very clearly. And cost, it can't really be a factor here. The old low impact development checklist often included statements that something was not economically feasible, and yet cost information was not formally reviewed. Previously, there may have been a site-wide variance allowed, but now the rule located at section 4.6 states, a municipality's approval of a variance shall apply to an individual drainage area and design and performance standard, and shall not apply to an entire site or project unless an applicant provides the required analysis for each drainage area within the site and each design and performance standard. There's a lot more to the mitigation requirements that must be met to obtain approval of a variance in the amended version of the rules. Mitigation must be part of the municipal stormwater management plan and follow these new requirements. Must be selected from the municipal list of mitigation projects, or it could be proposed by the applicant if it meets the criteria for the municipal mitigation plan. Must be approved no later than the preliminary or final site plan approval. It must be located in the same HUC 14. It must be constructed concurrently or prior to the major development. It must meet the green infrastructure standards, and the entity assuming the responsibility of maintenance for the project must submit a written agreement to the review agency. And lastly, the approved variance must now be submitted to the county review agency and DEP within 30 days of approval. Mitigation is required to receive a variance from the green infrastructure standards, but be aware that certain BPs cannot be used as mitigation measures and that there are minimum sizing and drainage area limitations. Note that vegetative filter strips and grass soils are excluded as mitigation measures, and they don't address quantity control and groundwater recharge. Green infrastructure BMPs that are used for mitigation need to be sized to manage the water quality design storm at a minimum and are subject to the specified drainage area limitations. Variances from the other standards are as shown on this slide. Note that there is no waiver or variance allowed for groundwater mounding. That's because the steps listed in Chapter 13 of the BMP manual make it clear that if the selected BMP fails to pass the groundwater mounding analysis, another BMP must be selected and assessed, meaning that a whole redesign is going to be required. The reviewer should also be able to determine whether linear development exemptions exist on the site. The following linear development exemptions may be granted if the requirements are met for each. And those are the construction of an underground utility line if revegetated upon completion, Construction of an above-ground utility line if the existing conditions are maintained to maximum extent practicable, and construction of public pedestrian access if made of permeable materials and are no greater than 14 feet wide. And finally, the reviewer may allow waivers to be granted for the enlargement of a road or railroad or the construction or enlargement of a public pedestrian access if the requirements here are met. And they are as follows: the public need for a project that can't be met another way. Design and performance standards met to the maximum extent practicable. Meeting these standards would require condemning existing in-use structures, and the applicant does not have and cannot get rights to other lands for mitigation. These specific exemptions were discussed earlier in Module 1. Water quantity is exempt if it's in a tidal flood hazard area and flooding will not increase. Water quality is exempt if the site has a NGIPD's permit with specific effluent limits. And groundwater recharge is exempt for previously developed areas in urban redevelopment areas. The last one, it's also going to be discussed in part 2 of how to review a project, so I'm not going to get in depth with that, but the reviewer must be aware of it. It is important that the reviewer is aware of what urban redevelopment exemptions are and where they can be applied. Urban redevelopment exemptions can only be granted to previously developed areas of a site. The existence of woody vegetation is a telltale sign of whether this exemption can be granted. If the reviewer finds that woody vegetation has returned to areas of a previously developed site, this exemption is not going to be allowed. Removing woody vegetation and putting new construction over this portion of the site will result in a loss of groundwater recharge. So that is why. The reviewer can check the NJGeoWeb to determine whether the rest of this information is applicable to the site. So in summary, the following are the possible variances, exemptions, and waivers that may be applicable to the site, but it's important that the reviewer takes the time to make sure that they can be applied and that they are only applied to the specific portions of the site that meet these specific requirements. So moving on, the next thing the reviewer should be looking at is if the applicant is meeting the design and performance standards using green infrastructure. The rules require that the design and performance standards are to be met using GI. And the rules require that GI BMPs be used to address the requirements for groundwater recharge, stormwater runoff quantity control, and stormwater runoff quality. Subsection 5.2 of the rules includes 3 tables, and they list those BMPs that may be used to meet the design and performance standards. The tables found there specify information on how each BMP may be used. And Table 5.1 coincides with Chapter 9 of the BMP manual, which are the GI BMPs. And they include cisterns, dry wells, grass swales, green roofs, GI MTDs, pervious paving systems, small-scale bioretention systems, small-scale infiltration basins, small-scale sand filters that are GI, and vegetative filter strips. Some of the BMPs cannot receive runoff from motor vehicle surfaces and therefore do not address water quality, and those are like cisterns and green roofs. Others don't offset the discharge of stormwater runoff from the 2, 10, and 100-year design storms, so they cannot meet the quantity control requirement. And something like that is like a dry well. And not all MTDs are considered GI, but the ones that are considered will be included here in Chapter 9. These MTDs have a vegetative or soil component that meet the GI definition. And lastly, these small scale systems listed here, they have a limited drainage area that they can treat compared to other BMPs. And as you can see, the column on the left includes the name of the BMP, and the column on the right includes the maximum contributory drainage area. So for example, if you're using a dry well, the maximum contributory drainage area is going to be an acre, MTDs, 2.5 acres, and so on. Note, this is table 5.1. So again, we're only talking about MTDs approved for GI. In the past, we've seen projects that propose to design two small-scale GI BMPs that each have drainage areas just less than the maximum allowable contributory drainage area. They would be side by side in a corner of the site so as to try and get around the drainage limitation. However, a design like this is not going to meet the GI definition. Just a review, green infrastructure means a stormwater management measure that manages stormwater close to its source. So the design of small-scale GI BMPs shall be distributed throughout the site and manage the runoff closer to the source that is generating the runoff. As you can see from the first diagram, the GI BMPs, they're all clustered together in the back towards the top of the picture. The second diagram shows two large-scale BMPs in proximity of each other. These BMPs would need to be spread out from each other to cover the entirety of the runoff of the site. Chapter 10 BMPs can be used to address stormwater runoff quantity control. These BMPs can have larger contributory drainage areas that the BMPs listed in Chapter 9. Chapter 10 BMPs include bioretention systems that are large-scale infiltration basins, large-scale GI sand filters, standard constructed wetlands, and GI wet ponds. Note that though I said they can address quantity, these BMPs may only be used to meet water quality and recharge if a waiver or variance is granted. BMPs in Chapter 11 are non-GI, and they always require a waiver or variance before they can be used. It's not anticipated that these BMPs will be used much in the future because of what is required in order to grant a waiver or approve a variance. But as for some of the BMPs noted on this table, blue roofs, they don't have a reuse component, and extended detention basins are typically large and require additional treatment to meet the water quality standards. The majority of MTDs currently do not have a soil or vegetative component, so they will fall onto this table here in Chapter 11. And then you see non-GI sand filters, subsurface gravel wetlands, and non-GI wet ponds to round out Chapter 11. So the next thing the reviewer needs to look at is stormwater runoff quantity control. Water quantity impacts must be addressed to not only prevent increased flooding due to development, but also to avoid increased flow rates, which can significantly degrade water bodies downstream from a site. In Module 1, we did cover the different options a designer can choose to follow. I'll briefly go through the options to meet water quantity control, as we have found this to have been done incorrectly in many of our reviews. It is important to note that the reviewer must make sure that all points of discharge from the site must meet the water quantity control standard, and if not, then the project is not going to be compliant. So let's begin with taking a look at the topography. Topography is important in identifying where the stormwater flows and is required to determine drainage areas and the time of concentration. Reviewers should be able to find the topographic information on the plans and make sure that it's accurate. This in some cases may even require the reviewer to physically see the site as well. It's often difficult for us to find drainage maps in these stormwater reports. We also see situations where the drainage calculations in the reports do not match up with the drainage maps in the plans. We need to see existing and proposed contours. We need to see the point of analysis, TC flow paths, and the drainage area to each point of analysis. The reviewer must be sure that the data used in the calculations matches the various maps and plans. This information must also be included on the drainage plans. It's very important to understand that each drainage area needs to be calculated separately. The reviewer should see the following calculated separately for each drainage area and must check the calculations for each drainage area. You should not assume that if one calculation is correct, then the rest are correct as well. So here's an example site. The flow was evaluated as sheet flow directed primarily in a southerly direction. However, we received complaints of flooding along the road lying to the east of the project and from the area northwest of the project. It was determined that the drainage areas were not delineated correctly. Whether or not this was due to an incorrect evaluation of the topography, that's unknown, but this does show why it is important to properly evaluate the topography and delineate drainage areas. To prevent those issues from occurring, the reviewer must verify that all drainage areas are outlined correctly, the proper time of concentration flow path is used, and the time of concentration is calculated properly. The reviewer needs to make sure that any natural ponding on site is included in the model. This is often overlooked, and ignoring it for the existing condition means the allowed proposed volumes would be larger than they actually should be. So on the same example site that was shown before, there was a 6-inch deep ponded area within the shape depicted. This was ignored, and the basin was made significantly larger than was actually needed. If there are any questions as to whether areas of ponding exist on site and it cannot be determined from the photos of the site, you may actually have to go there in person and see. The reviewer should be checking land cover next. Land cover should be clearly marked on the plans and be specific to what the land actually is. It should also include any existing BMPs that are on the site. The reviewer must verify that the plans and cover descriptions in the report match what is actually on the site. Aerial photos can be used to make sure the most pervious cover that existed in the past 5 years has been used in the calculations. Again, it may be necessary for the reviewer to verify the land cover conditions in person to make sure that they have been accurately described. Lisa went through how to determine soils, but just to reiterate, it is important to make an accurate determination of the soil types on site. The type of soil will greatly affect the functionality of the BMP. So again, the reviewer can find soil info at the NRCS Web Soil Survey webpage at the link provided right here. If information on these site soils cannot be found, you can use the methods found in Chapter 12 to determine the hydrologic soil group, either from the default HSG method or from soil testing. Making sure that the soil data for the site is accurate is a critical part of the review process. Inaccurate soil information can make or break a stormwater BMP, so a good practice generally is to review soil testing first. The rainfall depth and intensity information should come from these sources. You'll need to make sure the current precipitation adjustment and future precipitation change factors are appropriately applied for the 2-year, 10-year, and 100-year storm events using these tables on the slide, which are found in Chapter 5 of the BMP manual. NRCS has developed distributions for New Jersey, including NOAA C and D, which the BMP manual requires use of. These are already built into many stormwater modeling programs, such as HydroCAD. The reviewer should check that the correct distribution is selected, dependent upon where the site is located. The reviewer should next look at time of concentration. Information on how to calculate it can again be found in Chapter 5 of the BMP manual and the National Engineering Handbook. We also need to determine if the time of concentration in the pre-construction is appropriately calculated. We need to make sure that they are not underestimating this value. And we need to make sure that the Manning sheet flow roughness coefficient is 0.4 or less for the TC calculations. So according to the NRCS, the maximum Manning's roughness coefficient that can be used is 0.8 for woods with dense underbrush. But in New Jersey, we will not be using that. We do not have that situation. So the maximum Manning's roughness coefficient for sheet flow in New Jersey that can be used is 0.4. Anthony covered this in Module 2, and more on this is found in Chapter 5 of the BMP manual. As a reminder again, you will need to use the current precipitation adjustment factor and future precipitation change factor tables that are found in Chapter 5 to calculate the travel times for current and projected storm events using the 2-year 24-hour storm event, which will be used to calculate the P2 parameter. So look back through the handouts for the calculations presentation for Module 2 for more information on the correct way to calculate time of concentration. In summary, the reviewer must make sure that the sheet flow, shallow concentrated flow, and channel flow inputs are all correct. They must make sure that the proper time of concentration was used with the corresponding method. They must check the pre-construction time of concentration calculations, and the reviewer must now check the post-construction TC calculations, as it is no longer allowable to be assumed. Curve numbers are associated with the NRCS methodology and are used to calculate the amount of runoff caused by a specific amount of precipitation. The reviewer must be sure that the curve numbers correspond with each specific area based on land cover and hydrologic soil groups. The curve numbers are based on a presumption of a good hydrologic condition unless the design engineer provides evidence showing different conditions. Again, this was covered in Module 2. Here's an example of what a land cover table might look like from an engineering report. You see here the land cover, the area of the cover, soil types, HSGs, and associated curve numbers. The reviewer must check these numbers and land cover types against what is shown on the plans. Sometimes you could see that they do not match up necessarily. So always check, make sure that they correspond to each other. In all, the reviewer must check that curve numbers are justified in the report. You can verify these in the National Engineering Handbook, and the reviewer is responsible for making sure the chosen values are reasonable and that they are accurate. Now I'm going to hand it off to Anthony Roblick, who will take you through the rest of stormwater runoff quantity control.
All right, thanks, Manesh. Let me pull up the slides here. Okay, so now we'll continue on with unit hydrographs. So we have the two types of hydrograph. We have the SCS hydrograph and the Delmarva hydrograph. And when reviewing NRCS method calculations, the SCS unit hydrograph should only be used outside the coastal plain area of the state, except in very rare cases where the design engineer can prove that the Conditions that characterize use of the Delmarva hydrograph are in no way present on a site within the coastal plain region of the state, or when the Delmarva hydrograph isn't permitted, such as when sizing an MTD. But other than those cases, the SCS unit hydrograph should not be used within the coastal plain. And correspondingly, the Delmarva hydrograph should always be used for sites within the coastal plain area. And use of the Delmarva hydrograph is actually only acceptable within the coastal plain. You can't use it outside. But whichever hydrograph is being used, the reviewer must make sure that the same hydrograph is used for both the proposed and existing conditions. So moving on to talk a little bit about runoff routing. So as you know, runoff from pervious and impervious areas is required to be routed separately, and this is something that is required in our stormwater management rules. It's the reviewer's job to make sure that this has occurred and that the areas are routed separately. This can be verified by confirming that the modeling printouts provided do not show a composite curve number. If the reviewer sees that a weighted average of pervious and impervious areas was being used, they should note that that is incorrect. And please take a look at Chapter 5 of our BMP manual if you're routing runoff from an unconnected impervious area. And the last point on the slide is if an off-site discharge point or a point of analysis receives runoff from several sub-drainage areas, then the peak flow rate at the discharge point cannot be a simple sum of the peak flow rates from each of the sub-drainage areas. The hydrographs from each sub-drainage area should be combined to find the peak flow rate at the discharge point. One situation that we often do not see correctly addressed is depression storage. So the reviewer should identify if any depression storage areas exist on site and that they are included in the model. Depressions can provide stormwater management benefits and should be protected if possible. One problem that arises from ignoring depression storage is in the pre-development condition is that it's not possible to accurately calculate time of concentration. So the reviewer must make sure that the depression storage is being modeled as an existing basin in existing conditions. So in general, this is the procedure to follow when reviewing existing condition depression storage somewhere within the confines of a proposed development. The reviewer must make sure that the depression area is modeled, the time of concentration is calculated from the outlet of the depression to the point of interest correctly, lag the depression outflow hydrograph by the calculated time of concentration, and then calculate the time of concentration for the remaining area of the site and route it separately. So this is the one example of depression storage that we saw earlier. Had this site been modeled accurately, accounting for the depression area, there most likely wouldn't be the issues that exist on site today. So when dealing with depression storage, the reviewer must make sure that there's the time of concentration to the depression area, calculate the stage storage data for the depression area, model the outlet from the depression area, and route the contributory drainage area to the depression area. So now we'll take a look at an example of depression storage, and this is modeled in HydroCAD. So the contributory drainage area, and here that's labeled as area EX2, is routed to the depression storage, and the reviewer can input the parameters in the HydroCAD or another H&H modeling software to make sure that the depression area was calculated correctly. So in this case, the depression is modeled as a small detention structure with 1,228 cubic feet of storage. And as you can see towards the bottom, the storage discharges over a 22-foot long broad crested weir. And the lowest elevation of the storage is at 49.1 feet. And the highest surface elevation for the 10-year storm, because this is for the this is a 10-year pond report, and that's at 49.64 feet. And all of these input parameters to describe the depression area are taken from the site conditions. So after having reviewed all of the input parameters, we should then review compliance with the stormwater runoff quantity standard. So option 1 is almost exclusively used for redevelopment, and Chapter 5 of the BMP manual includes a discussion and example illustrating this. As was mentioned back in Module 1, in order to meet option 1, the post-construction hydrograph cannot exceed at any point in time the pre-construction hydrograph, and that's going to be for both the current and projected 210 and 100-year design storms. So here's an example of a post-construction hydrograph exceeding a pre-construction hydrograph. And at first glance, the difference does appear to be negligible. However, the rules do not permit any exceedance. And if we were to zoom in on this hydrograph, which we'll do on the next slide, we would see that the post-construction hydrograph has a higher flow rate than the pre-construction at several points in time. And so when we look into the comparison of the hydrographs from the previous slide, we see that multiple values from the post-construction hydrograph do exceed those from the pre-construction. And the times of exceedance are shaded in yellow here on both the table and the hydrograph overlay. And although the peak flow rate for the post-construction hydrograph may be less than the pre-construction hydrograph, the difference in time of concentration under the post-construction condition is what results most likely in this exceedance. Okay, we're not gonna cover option 2 here since that was previously covered, and we're gonna skip on over to option 3. And option 3 is the most commonly used, although that does not mean that errors occur in its use. Option 3 requires reduction of the post-construction peak flow rates to the 50, 70, or to 50, 75, and 80% of the pre-construction peak flow rates. That's for the current and projected 210 and 100-year design storms, respectively. This option requires use of green infrastructure stormwater BMPs with that make use of a detention function and an outlet control structure to attenuate the flow. So here's a list of the various Chapter 9 and 10 BMPs that can provide detention or a detention function. So we see BMPs such as pervious paving systems, small-scale bioretention systems, infiltration basins. Note that the BMPs listed here are considered GI, which are required to be used to meet the stormwater runoff quantity control standard. And note that Chapter 11 BMPs, which are not listed here, would only be eligible to meet the stormwater runoff quantity requirement if a waiver or variance from 7:8-5.3 was granted. So as we mentioned earlier, the report shall provide routing calculations of all design storms for every sub-drainage area. The reviewer should check the inputs, check that the pervious and impervious surfaces are separately calculated, check that the correct NOAA rainfall distribution was used, either NOAA C or D, and check that the correct rainfall depth was input, whether from the NOAA precipitation frequency data server or from the county rainfall data, and that the correct current precipitation adjustment factor or future precipitation change factors are applied. Also check that the time of concentration was properly calculated, and lastly, for this slide, check that the time span used captures the full storm event and discharge, and it isn't cut short or truncated. So here's an example pond report. We'll take a look at this particular printout on the next slide, but on this type of printout, it's important to check that if exfiltration was used in the routing and whether or not that is permissible depending on the BMP used. We'll check that any orifice used is no smaller than 2.5 inch minimum allowed. And also this is where we would be able to check the BMP discharge rate for a given storm event and then compare that with the maximum allowed for the post-construction condition. So this particular pond report is for the 100-year design storm, and the inflow area is a 1/4 acre of pervious surface. On the printout, it shows that exfiltration was included in the routing calculation, and it's denoted as discarded runoff, and they used a 1.5 inch per hour exfiltration rate. Something else to note, that this BMP design does not infiltrate the entire 100-year storm into the subsoil. As you can see on this slide, primary means the discharge of the 100-year storm through an outlet structure and with a max discharge rate of 0.34 cubic feet per second. You will in most cases see a discharge in the post-construction condition. As was mentioned in an earlier module, infiltration of the entire 210 or 100-year storm is allowed only when the existing site conditions are such that no runoff leaves the site for the pre-construction condition scenario, thereby constraining the design to infiltrate 100% of the volume produced by the post-construction condition for the same design storm. So in this case, the maximum storm that can be entirely infiltrated is the largest storm event with no runoff leaving the site in the pre-construction conditions. Or if the volume of stormwater runoff to be fully infiltrated is required by law or rule implemented by the Pinelands Commission, the Highlands Council, or any other stormwater review agency with jurisdiction over the project area. So if a proposed BMP is designed to infiltrate runoff into the subsoil, then the reviewer must check the groundwater mounding analysis. If there are infiltrating BMPs on site and no groundwater mounding analysis was submitted with the stormwater report, then the reviewer should ask the design engineer to provide it. There should be a groundwater mounding analysis provided for each proposed infiltrating BMP. Often the groundwater mounding analysis will show the mounding as rising above the bottom of the BMP, which means that the runoff discarded through the basin bottom into the subsoil is reduced from what is assumed in the routing calculation. If this is the case, then the routing calculation must be adjusted to use a smaller exfiltration rate, which will result in more flow being discharged through an outlet control structure. And if more flow is discharged from the outlet structure, then you should also check to see if the peak flow rate from the BMP is still below the maximum allowable peak flow rate. And if the discharge flow rate is going to be above the allowable peak flow rate, then the basin size or the outlet structure may need to be adjusted to provide more storage volume during the design storm. So for GI BMPs, the detention component can be the detention of storage volume above the surface of the water quality design storm. For example, a small scale infiltration basin that is designed to have an outlet orifice at the maximum water level elevation of the water quality design storm can have additional outlets at higher elevations for attenuating runoff from the current and projected 210 and 100-year design storms. Alternatively, you may design an underdrain bioretention system with storage pipes below the basin to provide the detention space for the current and projected 210 and 100-year design storms. Take note that provided storage space for detention should be located within the footprint of the basin. Designing a GI BMP with detention component located somewhere downstream or otherwise outside of the basin's footprint does not meet the design requirements as stated in the BMP manual. Okay, now that we've covered stormwater quantity, the next section the reviewer should check is stormwater runoff quality. So the stormwater runoff quality requirements are shown here. For new development, the proposed design must remove 80% of total suspended solids and stormwater runoff generated from the water quality design storm from the net increase in motor vehicle surface. And although there is no numerical target, the reviewer must ensure that the design removes nutrients to the maximum extent feasible. And the threshold for the water quality requirement is a 1/4 acre net increase in regulated motor vehicle surface. So each individual drainage area must meet the 80% requirement unless there is convergence prior to discharge from the site. Drainage areas discharging to different locations cannot be averaged together. Additionally, water discharging within a riparian zone must reduce TSS by 95%. So regulated motor vehicle surface can mean more than just a brand new paved parking lot. It also includes pervious areas that are intended to be used by motor vehicles. Additionally, motor vehicle surface that is currently receiving water quality treatment by vegetation or soil, by an existing stormwater management measure, or by treatment at a wastewater treatment plant where that water quality treatment will be modified or removed, is also considered regulated motor vehicle surface, and it will count towards that quarter-acre trigger. So just a quick note on pervious paving systems, since we are seeing them used more frequently under the current rules. So the reviewer must make sure that pervious paving areas are treated as regulated motor vehicle surface when considering stormwater quality, so they count towards that quarter-acre trigger. However, pervious paving systems designed in accordance with the BMP manual can assist in providing the required TSS removal. So rooftop runoff. Runoff generated by a rooftop is considered clean because it's not typically a significant source of TSS. However, it can be a significant source of nutrients, which the reviewer should make sure is considered in the design. Because of this, pretreatment of rooftop runoff may be a requirement depending on the BMP used, and the reviewer should consult the BMP manual for pretreatment information. So in the previous modules, we talked about the water quality design storm, which is unique to New Jersey. It's the storm that introduces TSS into our collection systems and our waterways. It's nonlinear in its distribution, and it's fairly intense with 1.25 inches of rain falling in a 2-hour period. And here's a graph depicting the total rainfall from the water quality design storm versus time. And you can find this graph in Chapter 5 of the BMP manual. And you can also find these values tabulated in the stormwater management rules. Okay, and here is a list of the various Chapter 9 BMPs that can provide stormwater quality treatment. These BMPs are considered green infrastructure, which is required to be used to meet the stormwater quality control standard. Note that Chapter 10 and 11 BMPs, which are not listed here, would only be eligible to meet the stormwater quality requirement if a waiver or variance from NJIC 7:8-5.3 was granted. And the BMP manual is designed to help the reviewer identify the design criteria that must be met for proposed BMP to merit the approved TSS removal rate. So in addition to the TSS removal rates, there are phosphorus and nitrogen removal rates associated with almost every BMP in the manual. This is a table identifying the different rates associated with the different BMPs, and this information is included in Chapter 4 of the BMP manual. So as you may have seen quickly in that previous table, but not every BMP is rated for 80% TSS removal. Sometimes a series of BMPs are needed to meet the 80% TSS removal requirement or the more stringent 95% rate for projects discharging within the riparian zone. So when calculating the effective TSS removal rate from a series of BMPs, we use the equation in the third bullet point here, where A and B are the TSS removal rates from each of the individual BMPs. Something else to note is that when a combination of BMPs are used, justification for the placement order is needed, and that's according to the hierarchy seen here. So first considering TSS removal rate, and then nutrient removal rate, and then lastly considering ease of sediment and debris removal. Also, the reviewer should verify that 2 of the same kind of BMP are not used in series, as the downgradient one will not be as effective. And if we run through a quick example of calculating the effective TSS removal rate for 2 BMPs in series, in this case we have a vegetative filter strip, which by itself is rated for 60% TSS removal. And downstream of that, we have a small scale infiltration basin, which is rated for 80% TSS removal. And if we put them in series and plug in the values to the equation, we get a combined effective TSS removal rate of 92%. Okay, so moving on to nutrient removal. Nutrient removal is required for all major developments. As we saw a couple slides ago, some BMPs have adopted nutrient removal capabilities, but often the best way to handle nutrient removal is through source control. So BMPs being used to meet the water quality standard must be designed in accordance with the BMP manual. And alternative designs that deviate from the BMP manual requirements may be used, but these designs must be submitted to the department for approval. So in summary, when conducting a water quality review, the reviewer must ensure BMPs used on site to meet the stormwater quality standard are from Table 5.1 of the rules and are adequate to achieve the required TSS removal rate and are designed in accordance with the BMP manual. Ensure that stormwater runoff that requires water quality treatment is being treated, and ensure that a deed notice of the stormwater BMPs used on site is submitted for approval and recorded in the county clerk's office prior to the start of construction. So now moving into more specific details about the different water quality BMPs. There are some general design criteria that applies to all water quality BMPs. So all BMPs must drain down in 72 hours. If the BMP is installed adjacent to pedestrian traffic, the drain time would be 24 hours. All infiltration BMPs must have a minimum 2-foot separation from the seasonal high groundwater elevation. And under drain GI BMPs must have a 1-foot separation. So here are some of the most commonly used water quality BMPs. And under the current rule, we've seen a significant increase in the use of small-scale bioretention systems, pervious paving systems, and also green infrastructure MTDs. So every BMP in the BMP manual has a summary page. This is the page for small-scale infiltration basins. The paragraph at the top describes how the BMP functions to remove pollutants and lists a TSS removal rate. The table shown below the description lists whether a BMP can be used to meet each of the design and performance standards. And as mentioned previously in Module 1, the green leaf here denotes if a particular BMP meets the definition of green infrastructure, and any design type that does not qualify for this use will be noted here. If there's a TSS rating noted across from the gold % sign, that means that the BMP is rated for the TSS removal rate if all of the design criteria are met, and that's including there being a maintenance plan. Notice the title of this chapter is green, and there are different colors for the different chapters, with green being for Chapter 9, Green Infrastructure BMPs, blue being for Chapter 10, Green Infrastructure BMPs, and black being for Chapter 11 BMPs. And this is just a visual aid to help in grouping the different BMPs in our BMP manual and which rule requirements they would be acceptable or applicable to meet. So if we continue on with small-scale infiltration basins, they are a very common BMP for water quality treatment. Small-scale infiltration basins achieve the 80% TSS removal rate and may also be used to meet the stormwater quantity and groundwater recharge requirements. Under the current rules, only the volume generated by the water quality design storm may be infiltrated unless specific cases allow for the infiltration of the larger storm events as previously noted. And that means there should be one or more orifices or weirs in an outlet control structure to discharge the larger storms. And this type of basin also has additional design criteria in the chapter, which is critical to preventing the basin impairment or failure. And a failed or impaired basin would likely require retrofit or major maintenance at least. So during your review for small-scale infiltration basins, also check that the minimum thickness of the appropriate sand is present, and check that the basin is not used as a stockpile location during construction. Make sure there's anti-compaction language on the plans, and if they are using a subsurface infiltration basin, there is a 80% TSS pretreatment requirement to keep in mind. Also make sure the hydraulic conductivity testing was performed correctly and that the design rate used should be between a 1/2 inch to 10 inches per hour. So some things you should not see for small scale infiltration basins. If they are designed for water quantity, they must have an outlet structure for the larger storm events. The reviewer should also not see any underdrains or liners in the design, or any topsoil or vegetation in the landscape or planning plan. And there must be no standing water in the basin 72 hours after the precipitation stops. So here's an example of 2 infiltration basins. The top one is functioning correctly. As you can see, the bottom one has ponding at the inlet locations, and there's a lot of vegetation established. And this is a pretty big basin, so something to consider is, if there's vegetation, how will compaction from the vegetative maintenance impact the ability of the basin to infiltrate? And additionally, the vegetation that is breaking down in standing water forms a biofilm that can cover the sand layer and greatly reduce the basin's ability to infiltrate. And this is why the BMP manual does not allow for vegetated bottoms for an infiltration basin. All right, so moving on to small scale bioretention systems. So bioretention systems provide more variability to address the rule requirements and are also very commonly used. Shown here is the summary page for small scale bioretention systems from the BMP manual. As you can see in the table, this BMP can be used to meet the stormwater runoff quantity, quality, and groundwater recharge rule requirements. So small scale bioretention systems rely on healthy, dense vegetation. The type of vegetation and the thickness of the planting bed determine the TSS removal rate. And here's a table with some design parameters and the corresponding TSS removal rates. And this is taken directly from our BMP manual. So small scale bioretention systems can be a practical BMP to implement in urban areas. Rain gardens are a type of small scale bioretention system and are encouraged under the new rules. There are even types with under drains to help facilitate drainage. So small scale bioretention systems have specific requirements regarding the depth of the planning media and what the planning media consists of. This planning media is designed to support dense vegetation, but also convey stormwater. So the planning bed must be between 18 to 24 inches in depth, and the planning media has specific composition requirements. Take note that the composition of inorganics is measured by volume here, but the organics is measured by weight. Small scale bioretention systems also have specific requirements in regard to stormwater quality, depth, bottom slope, and the density of vegetation, which can all be found in the BMP manual. And the reviewer must make sure that this criteria is met for any bioretention system that is being proposed. Okay, so we covered 2 examples, small scale infiltration basins and small scale bioretention systems. But in general, all BMPs that infiltrate runoff have specific design criteria associated with them, which can be found in the BMP manual. And reviewers should be sure that the criteria is being met. So you want to consult the BMP manual for that. To go over some of the common design criteria, reviewers must check that the soil permeability was tested and that a factor of 2 was applied to any tested permeability rate to get the design permeability rate. Infiltration BMPs may have design permeabilities between 1/2 inch per hour up to 10 inches per hour. That was previously mentioned. Some other common criteria, BMPs designed to infiltrate must have 2 feet of separation from the seasonal high water table. When we get into the groundwater mounding analysis, which you can also read about in our chapter 13, you'll see that infiltrating stormwater causes a temporary and localized rise in the groundwater table. And if this rise is great enough, it can slow down the rate of infiltration so that the BMP may not drain within 72 hours. This means that the basin must be either enlarged or retrofitted. And that's why it's so important to make sure that the soil testing is done correctly and that the seasonal high water table is properly located. So lastly, when reviewing infiltration basin designs, make sure that anti-compaction language is present, along with post-construction soil testing. It would be helpful to include the drain down time information also in the maintenance plan, so that's easy to find when in the future during maintenance activities. And so that's it for how to review a project 1. Thank you for your attention. And here's our contact information should you have any questions. Changi, are there any questions in the chat?
I believe I already answered over them. So we will take 5 minutes break. Please come back at 2:16. Thank you. Okay, it's 2:16. We will continue the second presentation of Module 3. My name is Chenny Wu. I will continue the project, how to review a project, part 2. And the goal of my presentation is to learn how to review BMP for compliance with the design criteria in the BMP menu. And also I will address the MTD design, although Dr. McGee already mentioned MTD certification and verification yesterday, but my presentation is more focused on the MTD design. And the goal 3 is to learn how to review the safety requirements. And then the fourth goal is to learn how to the groundwater recharge spreadsheets. So in Module 1, you have learned that the BMP chapter are arranged in accordance with the order of BMP listed in table 5-1, 5-2, and 5-3. So here are the BMP chapter that and the corresponding tables in the stormwater management rules. And I want to emphasize that in each subchapter of chapter 9, 10, 11, each chapter has a section titled Design Criteria. A BMP needs to be designed to comply with those design criteria in order to be recognized with those assigned TSS removal rate. So this the table 5-2 that is for the GI BMP that can be used for water quantity compliance. And the BMP list in table 5-3 that would need a variance from the stormwater ordinance or from the rules in order to use those BMP lists here. And I want to highlight some design criteria of the BMPs. The first one is system. If you want to design a system, the storage volume needs to be at least for the runoff from the WQDS, but the system needs to be emptied by the reuse demand within 72 hours. And for the stormwater water reuse, demand is based on the lowest volume need that would occur over any 3 consecutive days during the year. For dry well, the maximum design volume is water quality design storm runoff volume, and not for the runoff from motor vehicle service, because the dry well cannot provide water quality treatment. And if the clean roof runoff intermingled with the runoff from the motor vehicle service, then it cannot be direct to a dry well. Although a dry well cannot be used to treat runoff from motor vehicle service, it can be treat a clean roof runoff, and you can use that parts of the to reduce the runoff for the quantity design. The next one is pervious paving system. If you design a pervious paving system, the storage volume needs to be at least equal to the runoff of the WQDS. And also in the calculation of runoff on the pervious paving system, although there's no surface runoff out of the pervious system, because it's all most of the pervious paving system would be designed to take the runoff into the storage area. But you need to use CN number 98, so the amount of the rain falling on the pervious surface can be calculated for the storage volume. So next one is small scale sand filter. And a small scale sand filter for GI purpose cannot be designed with under drain. So it has to be designed to infiltrate the runoff into subsoil. And for the vegetative filter strip, you have to remain the runoff as a shear flow throughout the vegetative filter strip area. So if you have roof runoff, if you have the piping system collect the runoff from, for example, a motor vehicle service, and you want to pipe the runoff into a vegetative filter strip area, that would be not allowed, because once the runoff being concentrated, it would not be able to spread out as a shear flow. And for the TSA remote rate and associated vegetative filter strip length depend on the vegetation, soil type, and the soil, hydraulic soil group, and the slope. So you can check out chapter 9.10 to find those parameters. And for the weight pound, in the GI rules, weight pound has been separated into a GI weight pound and non-GI weight pound. And we'll take a look at them. For the non-GI weight pound, that is the one that you probably haven't seen in the past. And you need to have the extended detention of the runoff. And there's a criteria for the non-GI weight pound. It needs to have a minimum a 1/4 acre permanent pool surface area, and it needs to be a minimum ratio of the permanent pool volume to the water quality design stone is 1:1, and excuse me, the minimum drainage area is 20 acres. And also it requires very low permeability soil, our impermeable liner. And if you want to use the non-GI weight pound, you need to receive a waiver or variance. And next one is the GI weight pound. GI weight pound is listed in table 5-2, which means it can be used for water quantity, but it cannot be used for water quality. So if you want to use weight pound, GI weight pound for water quality, then you need a waiver of variance from the rules. So in addition to the design criteria for non-GI weight pound, which means those permanent pool sizing and the ratio, GI weight pound needs to be to maintain at least a 10-foot wide area of native vegetation along at least 50% of the shorelines. And also need to include a stormwater runoff retention component that's designed to capture stormwater runoff for beneficial reuse, such as irrigation. And volume available for beneficial reuse should be equal or greater than 1.25 inches of the rainfall on the drainage area of the GI weight pound. And stormwater reuse demand is based on the lowest volume need that would occur over any 3 consecutive days during the year. But it may be increased on case-by-case basis, depending on how you want to use those reuse those stormwater runoff being collected in the GI weight pound. But the use for the beneficial reuse should not cause the water level to lower than the permanent pool water level. And for the GI BMP that infiltrate water quality design stone runoff into subsoil cannot provide the water quality design storm runoff to the GI wet pond for beneficial use, which means that if you have a small scale, for example, small scale infiltration basin on the upstream of GI wet pond, then the runoff from WQDS already being infiltrated by the small scale infiltration basin. So the amount of the runoff, the WQDS runoff cannot be counted as the beneficial use into the GI wet pond. And we want to address a little bit more the beneficial use of GI wet pond. And the most of the case we saw is that they use those collected runoff for landscaping irrigation. And the method to estimate the irrigation should be based on some reasonable assumption. You cannot randomly just assign values such as like 1 inch per acre per day to calculate the irrigation use. You have to demonstrate why is 1 inch per acre per day. And here's a reference. You may use it. NRCS has an NJ irrigation guide, which provides one method to estimate the irrigation need. If you want to use another method, you need to provide a well-recognized publication showing the method and the variable you are using in your calculation. And we will work on the guidance, but now we will consider a case-by-case basis. And if municipality, if you need our assistance, you can contact us. So for the NJ irrigation guide published by NRCS, it includes following steps. First of all, the first step is to find the available water capacity of the soil at the landscaping area and the measurements inch per inch. And then find the effective root zone depth of the landscaping vegetation, which is how many inches of root zone. And then you can, based on that, to calculate the consumptive use. And then you can, by the acreage of the area, you would be able to find the water volume per irrigation and the days between irrigations. And for the available water capacity, AWC, it can be found from web soil survey and use the weighted average within the effective root zone depth of the landscaping vegetation. The irrigation needs as beneficial use must be consumed by vegetation in 3 consecutive days. And evapotranspiration of the landscaping area has been considered in the consumptive use if you use the NJ irrigation guide. So you cannot count the evapotranspiration from the vegetation that already been counted when you use the guidance from the NRCS. But for the evaporation loss from the wet pond service, it can be counted as part of the beneficial use. So the next topic is the safety requirements, and it's in the rule NJAC 7:A-6.2 A and B. And there are requirements for as for the location of the trash rake and the spacing between the trash rake bars. And we incorporate those information in our BMP chapters. So please check that when you approve the stormwater management design. And for the small scale GI BMPs, you may see that those big trash rake may not applicable for those situations, and we do have other alternative way to meet the rule requirements. So please check out those chapters. And for the safety requirements, there's one escape provision in the rule, and you can. It's very obvious that you can look at the drawings. It's also in the rule and BMP, and you have to decide that that's when you have a permanent pool design of the BMP, and which now is more likely to happen when you have a GI wet pump. So next topic, I'm going to address the how to design an MTD. So for the GI MTD, after the GI rule has been adopted, for MTD to be considered a GI MTD, it should infiltrate runoff into subsoil and/or treat the stormwater runoff through filtration by vegetation of soil. So an MTD that uses a biofiltration media and can be configured above ground and incorporate tree barks, planter barks, or shrubs will meet the GI definition. Any MTD with biofiltration media that would be placed below ground as a vault without any vegetation can be considered as a GI MTD only if the MTD infiltrates stormwater into subsoil. And furthermore, for the below ground device, we need to meet the NJDP BMP menu conditions, and that the infiltration, the volume of the infiltration has to be at least the water quality design stone. And for the soil below MTD has to meet the tested infiltration rate at least 1 inch per hour. And also need at least 2 feet separation from the season high water table. And another category of MTD is the non-GI MTD, which do not infiltrate runoff into the subsoil or treat the stormwater runoff through the filtration by vegetation of soil. And so just a reminder that if the design proposed to incorporate MTD to meet the water quality design and performance standard, they must incorporate the GI MTD into the design unless a waiver or variance for using non-GI MTD is granted. And again, for the GI MTD or non-GI MTD, it must be verified by NJCAD and certified by NJDP. And you have to check whether there's been the certification, whether that's been expired. And for the maximum contributory drainage area for GI MTD is 2.5 acres. And for the MTD design that we have the MTD specifically tested. So the manufacturer's other model not listed in the certification letter, even though they are the same type, cannot be used to meet the water quality design and performance standard. Also, the MTDs were tested under specific configuration and installation specification. So MTD that deviate from the configuration or installation specification cannot be used to meet the water quality design and performance standards. So for example, MTD has a drawing in the certification that the testing approved report that shows only one inlet, but the same MTD shows on the site plan is to be installed with 2 inlets. Then the site plan, the MTD depicted on the site plan would not meet the requirements. If the sizing requirement in the certification letter indicate the sizing is based on the maximum treatment flow rate and also the maximum inflow impervious area, then the model selection must be based on the flow rate and the drainage area, which give the highest minimum configuration. We have those calculation example in the MTD certification letter. So when you sizing the MTD, we can see that normally the sizing is done by the MTD manufacturer, but you should double check that whether the sizing is correct. And for the more requirement for the GIMTDs, if that the GIMTD is tested and certified based on the treatment provided by the vegetation in the MTD, you will see the condition require the maintenance of 85% vegetation cover in the certification letter. So you definitely will have to maintenance plan. So the 85% vegetation cover is there to maintain the original design, the vegetation cover. And that means that you have to cover the MTD area with 80% vegetation. So there is a difference. So there's another design criteria in the MTD certification letters that MTD must follow in order to receive the TS removal rate. If it's underground, it needs to be designed to infiltrate entire water quality design stone in order to be recognized as a GIMTD and receive 80% TSA removal rate. And as we adopt the stormwater management rule the amendment being adopted on July 17, 2023, the amendment removes the rational method. So all calculation of the stormwater runoff should be calculated by NRCS method. The example, there's one example. Example 5-9 in chapter 5 demonstrate the calculation, how to use the, and also for the NRCS method, only, excuse me, SCS standard dimensionless unit hydrograph can be used. And the precipitation depth for the calculation of the time of the concentration should be the projected 2-year storm. So which means that you have to apply the future precipitation change factor in table 5-6 of the rules to the precipitation depth for NOAA or for the county data, and then you would get the 2-year projected 2-year storm. So in summary of the BMP design, the BMP must be designed to meet the design criteria in the BMP menu. And multiple BMP can be used in series when necessary. And Anthony has addressed how to calculate the percentage. Infiltration BMP require detailed soil permeability testing, as we have the minimum permeability rate for infiltration BMP. And for the detention BMP, which now means that GI weapon must calculate detention time to determine the TSA removal rate. And for the MTD design, you have to use the NRCS methodology. And next topic I would like to address is the groundwater recharge. And for the rule requirement, there are 2 ways to demonstrate the compliance with the groundwater recharge. One is to demonstrate through hydraulic and hydraulic analysis that the site and its stormwater measures maintain 100% of the average annual pre-construction groundwater recharge volume for the site, or infiltrate the difference in the projected 2-year storm runoff volume. So we would talk about the difference of projected 2-year storm difference first. It's a simple calculation because when you do the pre and post construction analysis of the runoff, you will know the volume difference. And but as our experience, to infiltrate the difference of the projected 2-year storm would result in a larger infiltration structure. And then the mounting would probably be larger and cause mounting to make the infiltration BMP failure easier. And for the calculation of projected 2-year storm difference, you should use the NRCS method. And then you have to all follow the those criteria as we in the rules and the NEH and NRCS method. And just one thing you have to, when you review a design, you have to check whether the curve number that is being used in the groundwater recharge will be same for as they use in the quantity analysis. And the other way to demonstrate the meeting of groundwater recharge standard is to maintain 100% of pre-development groundwater recharge, and which you will need to use the New Jersey groundwater recharge spreadsheet. And the first things you receive and you want to review the NJGRS, the spreadsheet is that you want to make sure that the pre-development versus the post-development land use input, and also have the BMP design information available. And here's the first page of the groundwater recharge spreadsheet. And the orange shaded area are for the inputs and the gray area are for the output. And then let's take a look of the input for the first page. On the left of the page, there are input for the pre-construction condition. On the right side, it's the input for the post-construction condition. And just note that the infiltration is not same as groundwater recharge. Infiltration is only the process to allow runoff into subsoil. For groundwater recharge, the runoff needs not only to be infiltrated into the subsoil, it has to pass the root zone. And so for the different soil, there are different depths of root zone, and also the different vegetation would have a different the water capacity needs. So the soil in the spreadsheets play an important role in the calculation of the annual recharge and the recharge provided by the BMP. So on page 1, there is an input for the municipalities for the pre and post development land cover and the soil and acres. So it's important to make sure that the municipality is where the project being located. It's often that the consultant company, they use the spreadsheet for different project, for the project side in different location municipalities, and they forgot to change that the municipality, and the municipality would determine the pre-development annual recharge amount. So it's important to make sure that municipality is the correct one. And the output will be after you input the pre and post, then cover soil, acres, then the output will be the deficit. And some notes here the soil and the land cover must match the site plan, and also that being in the routing calculation. And the soil determined by the soil survey of chapter 12. For most of the time, you will based on the soil survey. And but if the soil survey, for example, it indicates that the area is urban area, urban land soil, and without any information of the soil series or the hydraulic soil group, then you can either on the site to determine the soil series, but actually that would be very difficult. So you would have to use the, if you don't want to do a on-site the field test of the just to determine the soil series, then you have to use the chapter 12 defaults. And another note is that the areas should match. So if you see that in the pre-development is it says 10 acre, but in the post-development, the summary on the right-hand side is only 9 acre or 11 acre more, then you have to ask the designer to verify the information, the inputs. So here's right now, there is the default soil series for NJGIS. So here is after you completing the first page, then and you know the annual deficit volume, then you will continue on page 2, check the dimension of the BMP and location of BMP to determine whether the BMP you design will provide overcome the deficit. And there are some parameters that they are kind of complicated, but basically if you look at the spreadsheets, that the red letters on the spreadsheet on the second page shows the status of whether the calculations are correct. And one knows that when you input those parameters in the second page, the spreadsheet will automatically calculate whether the BMP provides sufficient volume, recharge volume, so you don't have to click those buttons. And one important factor is that the segment BMP means that where the post development site segment in which the proposed recharge BMP will located, and that will match the that would be the land segment on the right hand side of the first page, and use the segment number to specify where on the side the recharge BMP will be located. And if you don't know, for example, if it's just early planning stage, you can use set to 0. Then it will be average of being average of the multiple segment in the post development. And for the porous pavement, segment should be the impervious area of the post development.
Forage for the whole you. Weight Watchers, the care you deserve.
Okay, let's continue. So for the ABMP, that means that BMP area, and we know that it is the footprint of BMP excluding the sloped areas. And for the DBMP means the BMP effective depth and maximum equivalent water depth that can be achieved in the BMP before overflowing the begins. So if the BMP is filled with stone, the effective depth is the actual depth times the porosity of the filled stones. And for slope BMP, like bioretention swell, use the average dBMP, but you can adjust the ABMP to keep the ABMP times the dBMP should be always equal to the storage volume that's available for the recharge. And that's one one factor that's a little bit confusing. That means there is the dBMPU is the vertical distance from the vegetated ground surface to the maximum water level of the BMP. So if it's positive, means the maximum water level is below the ground surface, and negative is above the ground surface. And DEXC is the vertical distance from the vegetated ground surface to the bottom of the BMP. And let's take a look of these. So for this one, here, the first example is that the BMP has a vegetated bottom, so which represent the BMP like a bioretention basin. Our sand filter has a vegetated bottom surface. The input of dBMPU is the depth to the upper level, so it's the vertical distance from the vegetated ground surface and to the maximum water level in the BMP. So because the vegetated ground surface is below the water level, so the value is negative, like the figure shows here. And the second input is DEXC, so the depth of lower surface of the BMP. So it's the vertical distance from the vegetated ground surface to the bottom of the BMP. So in this case, because the vegetated ground is the same as the bottom of the BMP, so the DEXC is 0. And for this one, we shows another scenario, and the BMP bottom is not vegetated. And in this scenario, the vegetated ground level is assumed to be the ground level surrounding the BMP. It's not the burn, it's just like the ground surrounding the BMP. And then the vertical distance from the vegetated ground surface to the maximum water level in the BMP, which the scenario is positive because the vegetated ground is above the maximum water level. And for the DEXC, the vertical distance from the vegetated ground surface to the bottom of the BMP, which is the full distance from the bottom of BMP to the ground level surrounding the BMP. And this one is another scenario, such as the pervious pavement or underground infiltration basin. So the dBMPU will be the top of the gravel level, where the runoff is stored to the top of the ground level, and the value is positive. If the maximum water level in the gravel storage bed is not up to the top, then the dBMPU will be the maximum water level to the ground level, and the DEXC will be the bottom of gravel storage bed to the ground level. So the difference in input in the negative positive of the dBMPU is important, is essential to the recharge volume calculation in the spreadsheet. So let's take an example that for this one, the infiltration stone BMP over area of 6,000 square feet. So here the scenario is that there's a sand layer over here in the bottom, and then it has a water quality at level 12.5 feet from the bottom. But you can see that for the 6-inch orifice, the lowest orifice of this outlet control structure is at a level a little bit higher than the water quality design stone. So we have to use this elevation as for the maximum water level. So for this one, the DPMPU is the vertical distance from the vegetated ground surface to the maximum water level in the BMP. And because this BMP doesn't have vegetation on the bottom of the BMP, so the vegetated ground surface in this case is not on the bottom. It will be the surrounding ground of the BMP. So the DPMPU will be positive, and the DEXC will be from the bottom to the ground level of the surrounding area. So here DPMPU will be this number. And here is the volume design, and then you will have the DPM, the depth, as we say, is the lowest orifice. So the depth for the DPMP will be 1.36 feet. And the area, you can use the volume, the recharge volume, to divide by the DPMP, and then you will get the APMP. Then you can put those input into the spreadsheet. But if same configuration, but just you have a different type of BMP that has the vegetated button of the BMP button, then you will see the input are totally different. The DPM, although the DPMP is the same, but it's a negative value, and the DEXC will be 0 inch. So if you put those numbers into the BMP, the second page of the NJGRS, then you will get the different recharge volume, and you can place those numbers by yourself to see the difference. So again, for the groundwater recharge, the rule prohibit the recharge of stormwater with high pollutant loadings or industrial stormwater exposed to the source material. So for example, if you have a commercial site that that has a gas station, you should not direct the runoff around the gas station to the recharge BMP. And all recharge BMP must meet the infiltration criteria and design as that being put into the chapters. And if you have the if you design a recharge BMP, then all the you have to run the hydraulic the groundwater mounting analysis to consider whether there is adverse hydraulic impact on the groundwater table. So in summary, I address the BMP chapters. I highlight part of them, but please read those design criteria. And I also address the safety requirements and the MTD design and groundwater recharge. Okay, so there's my presentation, and let me take a look of the question in the post in the chat. Is any question that has not been answered?
Hi, Chang'e.
Yes.
We have a question about discharges to a vegetative filter strip. The question is, if piped runoff exists or exits to a riprap area before discharging into the vegetative filter strip, can that be considered sheet flow?
It cannot, because the riprap runoff from riprap would be either still become a concentrated flow, shallow flow, or sometimes it will become channeled flow. So it cannot be considered a sheet flow.
Okay, so the next question is in two parts, and it's about the beneficial reuse part of the GI wet ponds. So the first question is, what is the time period in which beneficial use water volume has to be used? And then from your slides, we saw that there was 3 days, but this person needs the location of it in the BMP manual. So I think we'll have to look that one up during the next break. Okay. Now, our next question involved the maximum treatment flow rate for the MTDs, and your slide 21 explained that the rational method is no longer to be used for sizing manufactured treatment devices, and so your slide also directs people to go to example 5-9 from chapter 5 to see the sizing calculation for the MTDs. And you will see now in the newer MTDs that are on our website, the certification letters have switched over to using the NRCS methodology rather than the no longer allowed rational method to calculate the flow rates. Okay, and then someone was asking, the next two questions are about recharge. So for historic fill areas that have heavy metal contamination, are they exempt from groundwater recharge?
The high pollutant could be including any chemicals or any chemical compounds that would consider as a pollutant. So if the heavy metal that's being classified as a pollutant, then yeah, it will be excluded. You cannot recharge the runoff from that area.
The last question is recharge related, but I'm going to ask the questioner to turn on his microphone. Brian Intandola, I'm not sure. Could you explain your question and ask it more directly? Or type in the chat and I'll read it for you. Because it seems to say if there's an EV station, can we recharge? So I'm trying to.
Yeah, I saw that question. If EV station, can we? EV station that doesn't have any. As I can vision, that doesn't have any like gasoline that would be contained in the runoff. So I think it's clean, right? So unless the EV station would produce any other pollutants, that would I cannot consider now. Otherwise, the runoff on the EV station should be have no problem to be recharged. And I saw there another question that related to the heavy metal. Is that the area? Yeah, you already addressed that, but I want to emphasize it's not the whole side, the historical field side that's exempt from groundwater recharge. Is that area will produce the heavy metal contamination, you cannot do the recharge. But for example, if there's a building, the area that would not have the heavy metal into the runoff, then the runoff in that area, if that create deficit, when you develop the area, you will have to recharge those runoff. So if there's no further questions, I think we will. Okay. I will answer the question later if you continue put into the chat. So we will continue the presentation of mounting analysis.
Do you want us to take the break?
I think we already take the break, right? So we can.
We're on par with the last version.
Okay, if we want, we can take a 5 minutes break. If everyone wish to, have a break. Yep, and right now it's 3:05. We come back to continue the presentation at 3:10. Thank you.
Thank you.
All right, hello everyone. It's Peter Planthos again from the Municipal Stormwater Engineering Unit. It's now 3:10, so we're going to continue on to the next presentation where we will dive into the groundwater mounting analysis requirements and calculations necessary for the use of infiltration BMPs. This material is covered in depth in Chapter 13 of the BMP Manual. My goal with this presentation is to cover the requirements under the stormwater management rules, as well as concepts, methods of calculation, and examples, all in relation to groundwater mounting analysis. Rules require we assess the hydraulic impact of the proposed development on the groundwater table and design the site to avoid adverse impacts. Well, in order to describe what is an adverse impact, let's take a look at what happens when we infiltrate stormwater. Below the surface, the groundwater table rises locally, and then it needs some time to spread out before returning to stasis. When we force a concentrated amount into one area, we get mounding. This increase slows down the ability of the basin to infiltrate. So we can have problems if this increase is large enough to slow down the rate of infiltration beyond our 72-hour window, or from repeating this slowing down over and over, the basin can experience failure. Additionally, as this mounding spreads out, it can reach adjacent structures such as basements and septic systems. Let's look at a nice graphic that illustrates this. This illustration is in the paper prepared by Glenn Carlton from the United States Geological Society, or USGS. We have a house near an infiltration basin. The blue color area below everything is known as the saturated zone, whose top surface is the seasonal high water table. Imagine, if you will, that it rained. The rain has now stopped and runoff has collected in the basin. As stormwater infiltrates below the bottom of the basin, we get a temporary localized increase, or mounding, below the basin that is caused by stormwater infiltrating into the subsoils after the storm event. In order to dissipate, the volume of water under the curve has to move outward and downward until it returns to how it was before the rain. We need to calculate the maximum height of the mounding in order to assess the impact of infiltrating stormwater on the basin and on nearby structures. One method of calculating the height of groundwater mounding is covered in Chapter 13. That method, known as the Hantush equation, dates back to 1967. It requires the computing capabilities such as that found in the Excel spreadsheet developed by the USGS. You basically enter in certain parameters and then click the Calculate button to see the results plotted. Additionally, the user gets results in the cells of a spreadsheet. There are certain ground rules, pun intended, for using the spreadsheet. So we'll go over what parameters we need to define, and then we'll look at making sense of the plot of the spreadsheet, the plot the spreadsheet creates by virtue of a macro. This is a screenshot of the Hantush spreadsheet. If you have used the spreadsheet in the past, you may find this spreadsheet a little bit different from the spreadsheet that was posted on the USGS website. That's because in March 2020, DEP published and adopted a new BMP manual chapter titled Chapter 13, Groundwater Table Hydraulic Impact Assessments for Infiltration BMPs, which provides both detailed guidance regarding the input values and examples illustrating how to conduct the groundwater mounding analysis. With permission from the USGS, we modified the spreadsheet. Here is how it looks today. All of the calculation algorithms are the same, but the units and the notes on the use of the inputs are modified to be consistent with other chapters of the BMP manual. Chapter 13 and this spreadsheet are available at the link shown on this slide. To get more familiar with the Hantush spreadsheet, let's define the parameters listed here and establish the assumptions for their use in the spreadsheet. The first input parameter is the recharge rate. In the spreadsheet, you must use the design value for the vertical saturated soil hydraulic conductivity, which is 1/2 of the tested value of the vertical saturated soil hydraulic conductivity from soil testing performed in accordance with Chapter 12 of the BMP manual. The second input is the horizontal hydraulic conductivity, which is rarely tested on the scale of a single site just for the purpose of conducting a groundwater mounding analysis. Therefore, you will need to use presumptive values based on the site's location. If the site is located in the coastal plain, then the horizontal saturated soil hydraulic conductivity is presumed to be 5 times the recharge rate, meaning the vertical saturated soil hydraulic conductivity. If the site is located outside the coastal plain, the horizontal saturated soil hydraulic conductivity is presumed to be the same as the recharge rate, that is, the vertical saturated soil hydraulic conductivity. If you recall, Lisa provided us in Module 2 with the link to the Bureau of GIS website where you can determine if your site is in the coastal plain. That link is also found on this slide. And you may notice on the slides that were provided to you that the hyperlink might not be working correctly. So someone from our staff will be posting the correct link in the chat for you all. All right, the next parameter is the specific yield, which is the volume of water that will drain from a soil specimen due to gravity divided by the total volume of the soil specimen. Coarse soil will likely have a higher specific yield than fine-grained soil having the same porosity. Specific yield governs how much water the unsaturated zone can store when recharge reaches the water table. The more water that can be stored in the unsaturated zone, the lower the resulting mounding. Therefore, a soil having a higher specific yield may result in a lower mounding height than a soil having a lower specific yield, when other inputs remain the same. For groundwater mounding purposes, specific yield is not calculated by subtracting field capacity from porosity. The hand-touch spreadsheet assumes that the BMP is rectangular in shape and the sides of the BMP are vertical. So we use the width and length of the bottom area of the BMP, also called the footprint, but since the mounting is highest at the center of the BMP, for graphing purposes, we use 1/2 of each dimension as the inputs for the length and width, which correspond to the X and Y axes, respectively, as the inputs. Now for BMPs of other shapes, like for circular shaped BMPs, you're going to want to use the radius of the circular basin as both X and Y. For irregular shaped BMPs, you're going to want to convert the shape to a rectangular shape that has the same depth of stormwater runoff to be infiltrated and is best fitted to the original shape. And then if a BMP is designed with sloped sides, you want to use the bottom footprint as the length and the width of the BMP and use the total volume of the runoff to be infiltrated divided by the area of the bottom footprint to calculate the duration of infiltration period. We will define duration of infiltration period in 2 slides, so bear with me. For the initial thickness of the saturated zone, unless proven by a field test showing the thickness of saturated zone beneath the proposed BMP, the default value is 10 feet. Note that the thickness of saturated zone used in the hand-touch spreadsheet is not the thickness of a large regional aquifer. It is the distance from the seasonal high water table to the first hydraulically restrictive layer. Now, if a value greater than 10 feet is used, it must be accompanied by on-site testing results that demonstrates the value used is appropriate. The input value must never exceed 75 feet, which is based on the preliminary results of research conducted by the USGS. The exact maximum allowed value may be subject to revision based on the final results of the research. Any on-site boring used to justify a value greater than 10 feet must be a continuous sampling boring for the entire drilled depth. The duration of infiltration period, T, is equal to the time required for the BMP to drain the volume of stormwater runoff at the specified recharge rate and is equal to the volume of runoff to be infiltrated divided by the product of the infiltration area and the recharge rate, where the volume of runoff to be infiltrated may be either the runoff volume produced by the water quality design storm or the volume of runoff to be discharged through exfiltration, if exfiltration of runoff during basin routing is used. The maximum duration of infiltration period that may be used in the hand-touch spreadsheet is 72 hours. When hydraulically restrictive soil layers are present below a proposed infiltration BMP, one solution may be soil replacement. Let's analyze how that may impact the input parameters. In the situation where the soil is replaced all the way down to the seasonal high water table, there are a couple of things to note. The recharge rate shall be 1/2 of the tested vertical hydraulic conductivity of the soil replacement media, up to a maximum of 10 inches per hour. However, the horizontal hydraulic conductivity shall be calculated based on the original soil, since the original soil will be surrounding the BMP outside of the soil replacement. The low permeability soil will still be present in the surrounding area, and the resulting horizontal hydraulic conductivity will still limit the ability of the runoff to be dissipated into the saturated zone and may result in high groundwater mounding in the unsaturated zone. Therefore, the use of soil replacement in basin designs must still be carefully evaluated with a groundwater mounding analysis. Example 7 in Chapter 13 of the BMP manual describes a groundwater mounding analysis scenario where soil is replaced down to the seasonal high water table below an infiltration BMP. And it is important to note that if a shallower depth of native soils is to be replaced, rather than replacing the soil down to the seasonal high water table, the recharge rate shall be 1/2 of the lowest vertical saturated hydraulic conductivity of the remaining native soil. Continuing on, there are some important relationships between maximum mounding height and the input parameters to note. Delta H max is the maximum height of the mounding, and the value calculated by the hand-touch spreadsheet is that which occurs at the end of the duration of infiltration period. This is explained on page 17 of Chapter 13. However, the hand-touch spreadsheet does not further calculate the mounding as it spreads out over time. We'll talk about this further in just a moment. A lower mounding height will happen when the horizontal hydraulic conductivity increases, when specific yield increases, or when the initial thickness of the saturated zone increases. You cannot just use the results from the spreadsheet as it appears. The results have to be checked against the physical constraints of the design. If you get a resulting mounding height that is higher than the distance between the basin bottom and the seasonal high water table, you do not get an artesian condition. It means the recharge rate is adversely impacted by a reduced hydraulic gradient and will be slower. That means you'll have to run the spreadsheet again after you make some changes. Because there is a proportionality between the recharge rate and the duration of infiltration, as shown in this equation, the changes include using a smaller recharge rate and a correspondingly longer duration of infiltration period for the same infiltration area and the same volume of runoff to be infiltrated. Furthermore, if the mounding height just touches the bottom of the BMP, the recharge rate will also be slower than the design value for the vertical saturated soil hydraulic conductivity. When this happens, you can stretch the duration of infiltration period while decreasing the recharge rate, or you can spread the volume of runoff to be infiltrated over a larger area. When opting to increase the footprint, you'll be able to use a shallower depth. There are some limitations associated with how the hand-touch spreadsheet operates. The graph produced by the spreadsheet is comparable to a snapshot in time of the mounding that occurs at the end of the duration of infiltration period. Since it's the snapshot, it does not depict what happens over time, as the mounding height decays and spreads out. During decay, while the maximum mounding height under the center of the basin will reduce, the mounding will expand into the horizontal direction and potentially cause the tails of the mounding curve to rise higher than the height at the beginning of the decay. This means that if an underground structure appears to be above the mounding predicted by the spreadsheet, or out of range of the mounding altogether, it may still be inundated when the mounding height decays, since the hand-touch spreadsheet does not provide the height of the tails of the mounding during the decay period. Therefore, caution should be used when applying the spreadsheet to analyze adverse impacts to subsurface structures in proximity to an infiltration BMP. Now that we better understand the inputs to the hand-touch spreadsheet and the results it provides, let's go to some examples that illustrate the method and what to do with the results. The examples presented today are two of the ones included in Chapter 13 and are arranged from simplest to more complex. After a straightforward example, we'll look at an analysis that shows infiltration will be at a slower rate than the design saturated soil hydraulic conductivity and what changes need to be made because we encounter an impact. In other words, we'll see two different scenarios. For the first example, a major development located in the coastal plain proposes an infiltration basin whose bottom footprint measures 50 feet by 50 feet to infiltrate 5,000 cubic feet of runoff generated by the water quality design storm. And a few other notes: the maximum depth of ponding water is designed to be 2 feet. The soil testing was performed in accordance with Chapter 12. The soil testing report shows that the seasonal high water table is 7.5 feet below the 6-inch thick bottom sand layer of the basin. The tested soil permeability rate of the most restrictive soil horizon below the basin is 4 inches per hour, and no nearby underground structures are present. All right, so let's start with some basic calculations. Typically, the soil testing provides results in inches per hour, so the value for T would also use hours as the unit of measure. For the duration of infiltration period, we'll divide the volume of runoff to be infiltrated by the product of the infiltration area and the recharge rate. Also, remember that the recharge rate is 1/2 of the slowest tested saturated soil hydraulic conductivity rate from soil testing. Therefore, the duration of infiltration period is calculated to be 12 hours. When using the hand-touch spreadsheet, it is helpful to make a table of the inputs and the results, so they are ready to be added in later to the report. These inputs are organized to follow the order they appear in the hand-touch spreadsheet. The recharge rate is the first parameter entered into the hand-touch spreadsheet, but it needs to be converted to feet per day if you are using the older version. Feet per day is just inches per hour times 2. So here we would use 4 feet per day for R. The specific yield is set equal to the default value of 0.15. The horizontal hydraulic conductivity is equal to 5 times the recharge rate, since the infiltration basin is located in the coastal plain. The basin measures 50 feet by 50 feet, so we would just input half of each of those dimensions since the analysis is performed at the center of the basin. And the duration of infiltration period is obtained from step 1. We also need to divide hours by 24 to get the number of days, which is 0.5 for this example, if we're using the older spreadsheet. And T is less than the upper limit of 3 days for the duration of infiltration period. And then lastly, the initial thickness of the saturated zone uses the default value of 10 feet. Alternatively, you can grab screenshots from the input section of the hand-touch spreadsheet, shown here with the parameter values from the previous slide entered in the gold shaded cells. This version of the spreadsheet is one that allows time to be input in hours rather than days, and recharge in inches per hour. With the inputs entered, I clicked the dark blue Recalculate Now button and took this screenshot after the macro finished plotting the blue curve. The results show in the red cell in row 16 the maximum height of groundwater mounding, represented by the variable delta H max equals 6.07 feet, which I've circled in light blue. And this is what will occur at the end of the duration of infiltration period. To put this into proper context, I've also superimposed a symbol representing 1/2 of the bottom of the basin. Since the seasonal high water table, which the spreadsheet always sets at y = 0, is 7.5 feet below the bottom of the sand layer, the temporarily elevated groundwater table, located at y = 6.07 feet at the center of the basin, where x = 0, will not reach the bottom of the sand layer. Therefore, the assessment shows no adverse hydraulic impact to the proposed infiltration BMP from the groundwater mounding. Remember that had the height of the mounding been high enough to intersect the bottom of the basin, it would mean the mounding will interfere with the infiltration capability of the basin. We would have to run a new model or trial that would involve increasing the basin footprint to spread out the volume of stormwater being infiltrated. That would result in a lower depth of stormwater runoff in the basin, since the volume is the same, and the duration of infiltration period would also have to be recalculated before the spreadsheet is run again with these new parameter values. If you recall the duration of infiltration period equation from slide 21, the footprint area is in the denominator, so we would see the duration of infiltration period decrease proportionally as the area increases. Next, we'll talk about when things go wrong, meaning adverse impacts. This slide is not for the example I just presented. It is meant to show you what happens in the spreadsheet when the groundwater mounding height is too high. If you click on the dark blue Recalculate Now button, and the results show delta H max in the area I've circled is larger than the distance from the seasonal high water table to the bottom of your BMP, you won't be able to tell just by looking at the graph. In this case, the seasonal high water table is 8 feet below the bottom of a basin that is 90 feet in length. The height of the mounding is calculated to be 9.51 feet. The plot by itself looks normal, but is it? We have to understand what is being plotted and check it against the reality of our design. The depth to the seasonal high water table is 8 feet. This does not mean groundwater will rise up in real life above the bottom of the basin like this. It means the temporary elevation in the groundwater table located at the center line and above the seasonal high water table will intersect and exceed the elevation of the bottom of the sand layer, meaning it interferes with the infiltration capability, and therefore it will take the BMP longer to drain. Adjustment of the basin design is therefore needed to reduce the impact of groundwater mounding. So we have to adjust our parameters and run the spreadsheet calculation again. To do that, we have to reduce the value for R. We don't know exactly how much it will slow, but my first attempt would try reducing it by 50%. However, we are not ready to click Recalculate. The horizontal hydraulic conductivity is not adjusted since it is not affected by the reduced hydraulic gradient in the vertical direction. But the duration of infiltration period must be proportionally adjusted to reflect this slowing down. For example, we will double the initial value for T if we halved R. Although we don't know the exact rate to which the rate will slow, even if it is slowed by 1/2, we're going to check the mounding for a value of T that is within the maximum allowable time period. Sometimes we call this stretching the infiltration period. Next, we would click Recalculate and check the result to see if delta H max is now less than the distance between the seasonal high water table and the bottom of the BMP. You might try this one more time with T a bit longer, as long as the value for R is proportionally reduced. If that doesn't work, you're going to check Chapter 13 for an example of changing the dimensions of the infiltration area. All right, with that explained, let's move on to our second example. We're going to look at a dry well for the example of an adverse impact. Even a small BMP can cause one. A site is located outside the coastal plain. A 7-foot high by 5-foot diameter dry well is proposed to store and infiltrate 137.4 cubic feet of roof runoff from a single-family home for the water quality design storm. The house has a basement floor located just above the groundwater table. The edge of the dry well is 10 feet away from the house. Soil testing was performed in accordance with Chapter 12. The soil testing report shows that the seasonal high water table is 2 feet below the bottom of the dry well. The tested soil permeability rate of the most restrictive soil horizon below the basin is 4 inches per hour. And then the duration of infiltration period comes out to 42 hours. All right, and keep in mind that the dry well is circular, so we calculate its area to be 19.6 square feet and input it into the equation to calculate that duration of infiltration period. Using the same type of chart, here are the values for our input parameters. 1/2, the slowest tested saturated soil hydraulic conductivity rate is used for the recharge rate in the spreadsheet. The specific yield is the default value of 0.15. The horizontal hydraulic conductivity is the same as the recharge rate since the site is located outside of the coastal plain. The duration of infiltration period is 42 hours. And the initial thickness of the saturated zone uses the default value of 10 feet. The results show the maximum height of groundwater mounding, 1.11 feet, that will occur at the end of the duration of infiltration period at the center of the dry well. The temporary groundwater mounding does not encroach upon the bottom of the dry well, where it would have impaired infiltration had the mounding extended that high. Are we done? No. The rules require we also check the impact to the adjacent structure. Recall that the vertical axis is situated at the center line of the dry well, and the groundwater mounding curve is symmetrical on both sides of the vertical axis. The basement is 10 feet away from the edge of the dry well, which is 12.5 feet to the left of the center of the dry well. The spreadsheet results indicate the water table is also temporarily raised approximately 0.4 feet at the basement wall location nearest the dry well, which is an adverse impact prohibited by the rules. Therefore, the dry well may need to be moved farther from the building to avoid the adverse impact caused by the proposed infiltration. Per the USGS paper, an increase of 0.25 feet or less is an acceptable depth for underground structures to be temporarily affected by groundwater mounding. The mounding height at 20 feet from the dry well is just less than that. But considering the limitations of the hand-touch spreadsheet I brought up earlier, it would be advised to place the dry well even farther than 20 feet from the basement, since the mounding decay, which is not modeled, may result in a rising of the groundwater level at the basement area higher than as it is shown in the hand-touch spreadsheet. This example shows that even a small infiltration BMP may have an adverse impact on nearby underground structures. If you haven't read it, Chapter 13 includes a lot more examples. Also, Chapter 5 includes examples with groundwater mounding analyses and includes exfiltration in the routings, which is allowed in certain circumstances for the green infrastructure BMPs. I want to thank everyone for your attention. Here's my contact information, and I will check with Changyi if we want to address any questions. Let me see if there's any questions in the chat here.
No, we will continue. Thank you, Peter. We will continue the quiz. Thank you.
All right. All right, so we'll move on to the quiz here, and we will be providing the direct link to SurveyMonkey along with the QR code in the chat in just a moment. Please stand by while Manesh takes control.
All right, thanks, Peter. So now it is time for quiz 3. I think you all know the ropes by now, so I'll move through these first few slides fairly quickly. As I'm sure you remember, you have the option to follow the link shown on this slide to open the training website in a new tab or on your browser, where you'll find the quiz links at the bottom, or you may use the camera app on a smartphone to scan the QR code found in the bottom right. Once you click on the link for quiz 3, you will be directed to the quiz, which is now open on SurveyMonkey. Note the quiz link and QR code will be posted in the chat by our staff. Also, make sure you click submit at the end of the quiz to get credit for completing it. You must answer every question before you can advance to the next screen and finally submit. And you may only take the quiz once. Here's everything all in one place. Just a reminder, the quiz link is also in the body of the email that was sent to you for the invite to this module. It is now 3:45. Please take the quiz and be back in 10 minutes. We will begin the review at 3:55. Thank you. All right, everyone. Hopefully you are all back. We will get started right now due to time constraints. It is getting a little late. So let's get started with our review. We'll go right to question 4. Which one of the following is not a green infrastructure BMP? And the answer is D. It is an extended detention basin. Question 5. When reviewing water quantity calculations, which of the following must the reviewer check for accuracy? And the answer is D, all of the above. Question 6. Which of the following conditions must be met when a stormwater BMP is allowed to infiltrate the entire runoff from the 2, 10, or 100-year storm? And the answer is D, all of the above. Question 7. What is required as part of the municipal stormwater management plan to grant variances or exemptions from the design and performance standards? And the answer here is C. It is a mitigation plan. Question 8. If you have an impervious surface that has existed for 10 years, but have removed the impervious surface prior to the submission of the application that includes a stormwater management review component, can you still use this impervious surface as an existing condition in the stormwater management calculations? And the answer here is B, you cannot. Question 9, true or false? If a project has been reviewed by the NJDEP Division of Watershed Protection and Restoration, formerly known as dealer or land use, the municipality does not have to review it for compliance with its stormwater control ordinance or RSIS. And the answer here is B, that is false. Question 10, which of the following would be exempt from the groundwater recharge standard? And the answer here is only B, previously developed portions of a site in a designated center. Question 11, true or false? Reducing impervious surfaces on a redevelopment project always meets the water quantity control standard. And the answer is B, that is a false statement. Question 12, can an infiltration basin be designed with a perforated under drain pipe as a means of discharging runoff from the basin? And the answer is B, no. Question 13, true or false? The TSS removal rate requirement must be met on each subdrainage area of a site unless the discharge from each drainage area converges to a single discharge point on site. And the answer is A, that is a true statement. Question 14, when can a wet pond be considered to be a green infrastructure BMP? And the answer is B, C, both these statements above must be met. Question 15, true or false? When the groundwater mounding reaches the bottom of a BMP designed to infiltrate, the infiltration into the subsoil would be adversely impacted. And the answer is A, that is a true statement. Question 16, what method is used to calculate the groundwater mounding height? And the answer here is B, the hand-touch spreadsheet is. So that's it for the quiz review. We do not have the time to go through the common design issues presentation, but the handout of this presentation will be provided for you for your own personal review. So that is the end of module 3. Module 4, our final module in this session, is this coming Thursday, May 9th at 1 p.m. As always, thanks for your attendance and participation.